Good morning again. We're going to do a couple of problems out of your textbook together just to make sure you guys are good on them. I'm going to suggest one of them for you to try to do on your own because it's a little bit more challenging. So I'm going to do 77 and number 81. So 77, these should be pretty straightforward. And again, I'm going to show you the shortcut to doing this once we get everything set up and do it one time all the way out. But A says calculate the pH of 0.55 molar HCN if Ka is 6.2 times 10 to the negative 10th. So what we're going to do here, just set up your ice table. We're going to say this is 0.55. The change of HCN will be minus X. Water doesn't matter. Hydronium and cyanide ions start at 0. Their change is plus X. Okay, so this is 0.55 minus X. This is plus X. This is plus X. Right, and we are going to assume that X is negligible, right? Okay, that it's so tiny that it's not going to have an effect on the calculation here. And so our calculation of Ka is equal to hydronium's concentration. Sorry, Ka is equal to hydronium's concentration times cyanide's concentration. Okay, divided by the acid's concentration, HCN. Well, setting that up and solving for this, right, which is going to be the same thing as this, okay, I should get rid of these, right there we go. Setting that up, it's going to be the square root of Ka times HCN's concentration. So that's just simply going to be the square root of, and then Ka here was 6.2 times 10 to the negative 10th. And the acid's initial concentration was 0.55. Okay, and plugging that into the calculator, let's see here. So let's see, square root of 6.2 times 10 to the negative 10th times 0.55. This is 1.85 times 10 to the negative 5th molar. And so pH is just negative log of that. Running out of space here, times 10 to the negative 5th. So pH for the first one should come out to be something like 4.73. Okay. And then for B, really what I want us to realize here, I'm going to shrink that down. And then for B, what we realize here is that ultimately this just becomes finding the hydrogen ion concentration and the anion's concentration is really just the square root of Ka times the acid's initial concentration. So we're just going to shortcut straight to that. We're just going to say that this, okay, is equal to square root of the Ka here, which is 0.16, times the acid's initial concentration, which is 0.044. And that is going to give us, let's see what this does, 0.16 times 0.044. This is 0.08, it's bad, 0.084 molar. And so pH is just negative log of that. And that's going to give us something close to 1.08 for pH. But it wants an answer of what's the POH. POH is 14 minus pH, so 14 minus 1.08 should be what? 12.92 should be the POH there. So those are your two answers there for the first one. Okay, and then for 82, acetyl salicylic acid, that's aspirin. There's its formula. It's the most widely used pain reliever and fever reducer. Find the pH of 0.18 molar aqueous aspirin at body temperature. Okay, so we're just going to shortcut this just like we did before. Instead of writing out the entire ice table for this, we're assuming that X is negligible, and then that this is just simply Ka times the concentration of HC9H7O4, right? which for this problem, it's going to be the square root of 3.6 times 10 to the negative fourth. Extend that on over times 0.018. And that's going to give us a hydronium ion concentration of, let's see, times 0.018. This is 0.0025 molar. And it wants to know the pH, so pH is just negative log of that. And that's going to give us, let's see here, something like 2.59, something close to that value should be the answer there for that problem. The one that I want you to try on your own, it's a little bit down here. Try doing 18.81 now. It's like the last one in the 18.4 video that I showed you on polyprotic acids. So that's what I want you guys to go try right now. It's a little bit tougher. It follows the exact same setup as the one from the end of the 18.4 video. So try to follow along with that. If you have questions, let me know.